Hello, everyone. My name is Qiushi Bai. I'm a PhD student from UC Today, I'm honored to present our work, Rainbow, a rendering-aware index for high-quality spatial scatterplots with result size budgets. This work was done jointly with my colleagues, Sadim Alsudais, Professor Chen Li, and Professor Shuang Zhao. So spatial data is really widely used in our everyday lives. For example, there are many location-based services, autonomous cars, mobile devices, and etc. They are producing large amounts of spatial data in a daily manner or even in hourly manner. All the spatial data are supporting lots of applications in our everyday lives, such as dining, traveling, social networks, and many, many more. And to explore and analyze this large amount of spatial data and to support all those applications, people have developed lots of interactive visualization tools. For example, the well-known Tableau shown in the middle is a commercial software to do this. DACGL is a web browser-based visualization tool developed by Uber. Matplotlib is one of the most commonly used visualization tool in the Python community. There are many, many more tools beyond this list. We also build an end-to-end system to visualize a large amount of Twitter data, which is called a Twitter map. I will first show you a quick demo of Twitter map to see where the problem of this rainbow paper comes from. So this is the Twitter map application interface. A user can input an arbitrary keyword in the text box. Here we use COVID as an example, and then we can submit. The Twitter map will send progressive queries to a backend database to compute the tweets that mentioned the keyword COVID, and the results will be transferred back to the front end progressively. Then the user can do arbitrary zooming and panning operations on the scatter plot. For example, I zoom here and zoom into a county level or even the city level. And even a user can mouse over a single point to see the individual tweet of that point. So the problem for this Twitter map system is scalability. When the result size of a keyword is very large, then transferring and rendering the points for arbitrary zooming and panning queries in an interactive speed become very challenging. Specifically, consider our three-tier architecture. We have a backend database to host the data and a server to serve multiple clients. When the server receives a query of keyword COVID from the user, it will load those COVID-related tweets from the backend database progressively and cache the result for future zooming and panning queries. We allow different types of devices to be the clients, meaning that a client could be a powerful desktop with a wired network, could also be a small cell phone with limited resources and an expensive wireless network. Then we found that to achieve this simple multiple heterogeneous clients architecture, some new problems need to be addressed. The first is the different devices have different resource limitations. For example, laptops have the resources to show hundreds of thousands of points, while the mobile phones might only be able to show thousands of points. But the problem is the dataset could be much larger than the number of points that a device can handle. As we have already seen in the demo, for the COVID-related tweets, it has already been several hundreds of thousands of points. But if we want to allow the user to explore our scatter plot on a cell phone, clearly we don't want the user to really load hundreds of thousands of points into her cell phone browser. So we need to consider a flexible solution that can allow the client to submit a number of points budget such that our visualization results should have a good quality, while do not overwhelm the client devices. The second problem we found is that there are too many different front-end libraries that can be used for different clients to render scatterplots. And also different front-end libraries may have very different rendering effects. For example, the left side is a scatterplot rendered by a front-end tool that we implemented ourselves using a colored pixel to show a spatial point very similar to a bitmap. And the right side is a scatterplot rendered by DACGL library, which is showing a spatial point as a circle of colored pixels with transparency. So as you can see that different front-end tools may have very different rendering effects for the same set of spatial points. The rendering effects could be as simple as the left bitmap way, could also be as complex as the DACGL way. And even only for the same front-end library, there could be many different parameters that will make the final rendering effects very different. For example, the shape of each point, the color of each point, and the radius of each point. So the front-end rendering cannot always be modeled as a simple bitmap, but could be very complex. And for different front-end tools to achieve a high-quality scatterplot might need different distributed points. Here, for this example, if we use the left side front-end library, the very dense regions might need not too many points because of its easily overplotted effects. Well, if we use the right side, more complex front-end library, the dense regions might need some more points. It can be overplotted much harder than the left one. And of course, if we use even more complex rendering ways, like different colors or different radiuses, the results could be very different. So to solve the aforementioned problems, we formulated our problem to not only consider the different rendering effects given different front-end libraries, but also consider the number of points in the final result as a budget, which means we need to allow the client to submit a result size budget when it sends a visualization request for arbitrary zoom or pan queries. Namely, given a dataset D, a rendering function R, and an error function delta, for an arbitrary zoom or pan query Q with its query range, and a result size budget, for example, no larger than 10,000 points, then we compute a scatter plot with no larger than 10,000 points and with a good quality. Our solution to solve this problem is called Rainbow. It stands for Rendering Aware Index for Big Scatterplot Workload. Rainbow is a general framework. The main idea is the following. It has two phases, an offline building phase and an online traversing phase. In the offline building phase, we first build a standard quad tree using the given dataset. The left side shows an example partition of the whole world using a standard quad tree. T is the root of the tree, which represents the whole world as a square. Then T is partitioned into 4 quadrants, A, B, C, and D. And then B is further partitioned into 4 quadrants, M and O, P, and so on and so forth. To build such a quad tree is very simple. If we insert a point into the quad tree, we first find the leaf node that this point belongs to, and then put the point on the leaf node. And if there is a capacity limit, for example, 2 points, then as long as a leaf node has more than 2 points, it will split into 4 smaller quadrant nodes. So the partition depths of different places in the quad tree are decided by the dataset. The right side shows the corresponding quad tree structure for the left side partitioning scheme. Then after we have built such a standard quad tree using the given dataset, at each intermediate node, we pre-compute some representative points and store them on the node. When we compute the representative points, we need to apply the given rendering function and the error function to make sure these representative points have a good quality to represent all the points in the whole subtree. How to compute the representative points for each node, we will discuss this shortly. On each node, we also store some meta information about how good quality of the representative points are. This meta information will be used in the online traversing phase. Then when a query comes to the rainbow, we do the online traversing. We traverse the rainbow in a top-down manner. We model a feasible result for the query as a tree cut. An example tree cut is shown here as the red curve. It has nodes A, M, and O, P, C, and D. Then the result set corresponding to this tree cut is just the union of all represented points on all nodes in the tree cut. For example, the tree cut shown here corresponds to a result set of all points on the nodes A, M, N, O, P, C, and D. For an arbitrary zoom or pan query with the result size budget, we traverse the tree in a top-down manner. We expand the tree cut iteratively. Since every time we expand the tree cut, the result size will also be larger. So we will stop the expansion until we get enough number of points in the current tree cut and return all the represented points in the tree cut as the result set to the client. Now let's talk about details of how to implement such an rainbow framework. First, let's talk about how to build a rainbow for a given dataset. So first, we build a standard quad tree by inserting the points in the dataset incrementally. For this process, we can adopt any existing method. I already mentioned the main idea of how to build a standard quad tree using a given dataset. The next, we need to compute the represented points on each intermediate node in the quad tree. Here, for simplicity, we will consider a case that we always select only one representative point on each node. Suppose we are at node N in the quad tree, and the region covered by this node N is omega N. Then in the dataset D, there are, for example, 5 points located in the region omega D, omega N. The set of the 5 points is called Dn. Then we first compute a rendering result of rendering all the 5 points in Dn for this small region covered by N. This rendering result is shown on the right. Then we traverse the 5 points in Dn, and for each point, we compute a rendering result of only using this point for the small region. An example rendering result is shown on the right. Then we can apply the error function to compute an error between the 5 points rendering result versus the only 1 point rendering result. And after we traverse all 5 points in Dn, we can find the best representative point. We call it a Pn that has the minimum error. Then we store this Pn point on this node N as the representative. And also we store this error value on node N as the meta information. In this example, suppose the red point is the best representative point Pn, and the 33 is the error between only rendering Pn compared to rendering all the 5 points in Dn. Then we store Pn on node N and store 33 as the meta information, which will be used later in the traversing phase. So after we have built the rainbow, now if the user submits a query with the result size budget, for example, 20, we will traverse rainbow in the top-down manner, and we expand the tree cut iteratively to enlarge the result set gradually. To expand the tree cut, we do a best first search. For each reiteration, we pick the best node in the current tree cut, and then use its 4 children to replace the node in the tree cut, and then repeat this process. Then the question is, what does the best mean here? So here we define a so-called benefit value for each node. How to compute this benefit value, we will discuss this shortly. But for now, we can just assume it is some value computed from the meta information on the node. And this value indicates how much benefit we can get if we expand this node to be its 4 children. For this example, suppose the current tree cut is the solid red curve. It has nodes A, M, N, O, P, C, and D. And since each node has only 1 representative point, then the result set corresponding to the current tree cut has 7 points in it. And we know that the user query budget is 20. It means we still have space to expand the tree cut. So we now pick the best node to expand. Here in this example, the computed benefit values are listed in small squares on top of each node. Node N has a benefit value 9, which means which is the largest one in the current tree cut. So node N will be expanded, which means we use its 4 children, UVWZ, to replace N. Then the new tree cut is now AM, UVWZ, OPC, and D, with a totally 10 nodes in it. And once we expand the tree cut to include the new nodes into it, we need to compute the benefit values for all the new nodes. In the example here, we need to compute the benefit values for nodes U, V, W, and Z. And then we find that still the current tree count has only 10 points as the result set, so we can continue to expand the tree count. Then we repeat this best first process until we get 20 points, which means we get enough points for the user query budget. Then we need to stop and return the current result set. There is also another stop condition, which is if we find all the benefit values and the current tree count are 0, which means the further expanding the tree count will not make the result better. So in this case, we also need to stop and return the current result set. Now let's talk about how to compute the benefit value for a node. The main idea of benefit is that we want to add as few points as possible into the result set, but to reduce as much error as possible compared to the current result. So we define two values, gain and cost. Gain means if we really expand this node n by replacing it with its 4 children, how much error can be reduced for this small region covered by n. So we use the error stored on each node n, which means how much error it has. We only draw the represented point on n to represent the whole subtree covered by n. Then subtract all the errors stored on its 4 children, which means how much error it has if we draw the 4 representative points on them to represent the whole subtree covered by n. In this example, gain is 27. Cost means if we really expand this node n by replacing it with 4 children, how many more points we need to add to the result set. In this example, we use 4 points to replace 1 point, so the cost is 3. Then the benefit value is computed as the gain divided by cost. Now let's take a brief look at the experimental results. We evaluated rainbow on Twitter dataset with 100 million tweets. We used the 2 rendering functions. The pixel bitmap is the one implemented by ourselves using WebGL, and the other one is deck.gl. We used the 2 error functions. One is AED, called the average Euclidean distance, and the other is mean squared error. We compared our rainbow with a baseline approach called quadtree plus random sampling. This is to use a standard quadtree to index the points, and for an online query, we retrieve all the points located in the query range and do a random sampling to return the result set for a given budget. We also compared with nanocubes, which is a well-known data cube-based index that store aggregated information on each node of a quadtree. We also compared with the AID star, which is a more recent work that balances the overhead of image tails and data tails on an R tree adaptively. Here's a brief explanation of the AED function. For a perfect visualization on the left, we compute the AED error for the approximation visualization on the right. For each point in the original dataset, we compute its distance to the nearest representative point in the approximate result set. For example, for point A in the original dataset, C1 is the nearest point to A in the approximation result set. Then the distance of A is from A to C1. And the AED is the average of all such distances in the original dataset. The first setting was using pixel bitmap rendering function and the AED error function. The 2 figures show the result comparing rainbow with the baseline quadtree plus random sampling. As we can see, for different result sets budgets, rainbow outperformed the baseline in all cases. It has less errors and had less query time. The second setting was using deck.gl as the random function and the MSE as the error function. The 2 figures show the result comparing rainbow with the nanocubes. Since nanocubes does not support an arbitrary result size budget, we first got the results from nanocubes for a given range query, and then use the result size from nanocubes as the result size budget to query rainbow. In this way, we make sure both approaches returned the same number of points. As we can see, for both the quality and query time metrics, rainbow outperformed nanocubes. We also evaluated the construction time of rainbow index compared with nanocubes. The results show that for different dataset sizes, rainbow took less time to build the index than nanocubes. For the index sizes, Now, surprisingly, Rainbow was about twice as big as nanocubes. The reason was because Rainbow had to store lots of additional points on the quadtree nodes, while nanocubes only stored an aggregated value for each quadrant node in the quadtree. To conclude, Rainbow is a general framework for indexing spatial points. It supports arbitrary zoom and pan queries, multiple client devices with different result size budgets, high quality for different front-end tools, and less than half-second interactive query time. Thank you very much for your time of attention.